This lecture is being brought to you in part by the generous gifts of these sponsors.
Hi guys, thank you Ken for that welcome. I'm going to be talking to you today about improving human performance through wearable robotics. And by wearable robotics, I really just mean exoskeletons in general. So the first question is, what are exoskeletons? And when you type this into Google, you get a lot of things like this, which are a lot of bugs. The exact definition is that an exoskeleton is a rigid external covering for the body in some invertebrate animals, especially arthropods, providing both support and protection. And this was a very confusing thing for a lot of my soccer player friends. They were all in biology, and so when I told them that I couldn't come to a game because I had blisters from the exoskeleton, they were very confused. And exoskeletons have been in media quite a bit. We see them all over the place in Hollywood. Iron Man's possibly the most famous exoskeleton out there. And we have all seen this. It is very far in the future though, and we're nowhere close to this. We've also seen exoskeletons in Alien from 1979. When I told my mom I was getting a PhD in exoskeletons, she was incredibly confused because she saw Sigourney Weaver wear this device in the 70s. And then the final device I'm going to show from any sort of TV or Hollywood, this is possibly the most realistic, I would say. It's from a TV show called The Expanse, and it is an exoskeleton that looks amazingly similar to the one that we've developed here. So now that we've gotten through what exoskeletons are in the media, what some of our goals could be, I'm going to talk about exoskeletons in their current state of research and just sort of how do they work, what are some basics behind these devices. And exoskeletons work by targeting specific joints. So here on the far left, we've got an ankle exoskeleton. In the middle, we've got a hip and ankle exosuit. And so this is a soft device instead of a rigid one. And then on the far right, we've got a hip, knee, and ankle exoskeleton. All of these devices aim at different aspects of gait, of different types of locomotor capabilities. There are also very different actuation mechanisms behind exoskeletons. On the left, we have a passive device that uses your natural walking mechanics to be able to inject energy into the system. So there is no motor, there's no battery, it's just a spring with a clutch, and as you're walking, it gives you a little bit of a boost, and depends totally on your natural kinematics. And then on the right, we've got a powered exoskeleton. And this device does have motors and batteries. It's much more complicated because it's a larger space that we can search through. It gives us a lot more flexibility so we can do more with it, but it also makes it a larger challenge. And I have to plug my graduate research a little bit. We have also tethered devices as well as autonomous devices. So the tethered device on the left, the motors and power are actually in those black boxes in the back. Each motor weighs about 50 pounds. It's 7.5 kilowatt motor. There's 10 of them, so it is incredibly impractical to put on the device. But it does give us a lot of flexibility to be able to see what is useful in an exoskeleton. We can have as much torque and power. We have all the capabilities we could want, and we can use that to figure out what's useful and then design a device in the future that's able to handle those capabilities. Which is very different from the device on the right. All of the motors and power are on board on that backpack. So this device is able to go out into the real world. It's able to go out and do all kinds of different activities, whereas the device on the left is constrained to the lab space. So pros and cons of both design approaches. We've also got rigid exoskeletons and soft exosuits. I kind of alluded to this earlier. There's pros and cons of both. The rigid exoskeletons tend to have explicit joints. They can have larger torque and power capabilities, while the soft exosuits are usually lighter weight, much more form-fitting, much more comfortable as well. So the pros of the soft suits are they are easier to wear. You could also potentially even wear these underneath your own clothes, so you wouldn't be able to see them. But the rigid exoskeletons have the potential for more benefits because they're able to just do more to your system. And then these are some military application exoskeletons. They're very, very high torque, very high capabilities. And I mean, the one on the left is my right. I think it's about 200 pounds, and so it's just very large and heavy. We've also got exoskeletons in medicine. This is the indigo exoskeleton. It's intended for people who have a spinal cord injury, who've had a stroke, other types of neurodegenerative diseases, and it does all of the walking for you. So it's called position control. It moves your legs through space in a very specific pattern. This is another exoskeleton in a similar sort of vein from Exobionics. It is also for people with spinal cord injury and does all of the walking for you. And you do use crutches with these devices because they're not balancing on their own. You need to be able to balance with those crutches. This is the last device in this range that I'm going to show. It's called a rewalk, and it once again is for people with spinal cord injury. It's really common in a lot of rehabilitation settings. And then this device is a little bit different. It's called a locomat, and one of its objectives is to help with gait retraining. For people who've had a stroke, you have asymmetric gait, and physical therapists tend to place your foot to help you relearn how to walk. And the idea behind this device is to have a robot do that instead of a physical therapist and help you to walk much more symmetrically and rebuild that symmetric gait pattern. So to wrap up all of this, exoskeletons can have very different purposes for what application they're targeting. They could augment user performance by increasing strength or endurance. They could also help promote healthy aging. So one idea with that is to help reduce joint loading, which could be helpful for people with osteoarthritis. Another idea is to use these devices in a resistance type of mode, so we could help to maintain healthy muscle mass with having just a little bit of resistance as you're walking. And then the final option that I see is we can use these devices to enable mobility. So I've mentioned spinal cord injury quite a few times. Being in a wheelchair, it is constraining and it's harder to get around in a world that's built for bipedal locomotion. So if we could have this device that helps somebody to be able to get up and out of a chair, it could help them interact with the world in a much more functional way. Which I'm going to start with our research in this area. We have two different devices at IHMC. The one on the left is our custom in-house exoskeleton called Quix, and the one on the right is the rewalk that I showed before. So we've been working on Quix for about 10 years now. It's the 4th iteration of this device, and rewalk has been FDA approved for about 11 years. And there's some clear similarities and differences. They both have the ability to do all of the walking for you. They move your legs through space and have very large torque capabilities. And you also use these crutches to be able to self-balance. And the actuated directions, they are actually, I'm going to have to scoot over a little bit, but the hips and the knees in the sagittal plane, which is this direction, both of them have that direction actuated. The rewalk has a passive ankle, which means it's basically a spring, and so as you roll over your foot, it builds up a little bit of spring resistance and then helps to propel you forward as you're walking. And the IHMC device on the left, instead of having that passive ankle mechanism, it is active. So it is able to apply dorsiflexion and plantar flexion torque to help you with moving. And at least in able-bodied walking, the ankle does quite a bit for your energy expenditure. Let's see. They also have very different control strategies. So the rewalk has a watch that you are able to put the device into different modes. You can have it in sit mode, stand mode, or walk mode. And once you put it in that mode, it just goes until you tell it to stop. So you continue walking in a straight line unless you scuff your foot or tell the watch that you want to stop. The Quix, on the other hand, has all of the controls are on the crutch. So it's a little bit more on the user to be able to tell it what to do. You click a button every time that you want to take a step. You also have the flexibility to determine what kind of step you want to take. So it has the ability to change walking gait patterns for going up a ramp or upstairs. We also have the ability to do long steps or short steps or medium steps. So there's a lot more flexibility with Quix, but it's also very much a research device, and Mark, who's our exoskeleton pilot, is really the only person who's used it. The rewalk, on the other hand, is a rehabilitation device, and so many people have used it. It's in a lot of research labs as well as at the VA, and a lot of different people have been able to use this device. There we go. It's an experiment that we ran with the rewalk to be able to see what sort of physiological demand is required from this walking activity. So we've got EMG sensors on his arms to see how much force he's applying through those crutches. The crutches are also instrumented so we can see the real-time force feedback. And we're measuring his energy expenditure through that mask on his face. And I've got the watch, and I'm telling the device when to be walking and when not to. And it's a very challenging way to walk, but it's also very exciting because people are able to get up and out of the chair. Thanks. Give it a second. The videos are large, so it's slowing down my computer. We've also competed in quite a few different exoskeleton competitions. We competed in the 2016 and 2020 Cybathlon, and these are basically like obstacle courses for exoskeletons. They are very everyday tasks that we do regularly, like walking on a slope, as you can see on the far left, or walking over uneven terrain. But with a wheelchair, they're not quite as feasible to be able to do these things. So these obstacle courses are intended to see how far can we progress this technology, how good can we make this, and really push researchers to see what bounds they can get to. We also competed in the Mobility Unlimited Challenge from the Toyota Mobility Foundation, which was a similar sort of approach where they were looking for everyday tasks. Mark got onto a bus and off of a bus by himself. There's a video of him welding his own wheelchair, as well as making a cup of coffee in the break room. And the next few videos are going to showcase a lot of the different gaits that we have with Quicks. So here we've got Mark walking up a slope, over a flat ground, and then down a slope. And the gait pattern is different for each of these. Where going up the slope, it tilted his torso forward so that his center of mass is really over his feet, and it's helping to propel him up that ramp. And then when he's walking on the flat ground, he doesn't have to be leaned so far forward. He can walk much more upright. But then going down the ramp, he's using the crutch as well as the handrail to be able to brace as he's going downwards. And you can also see with his feet how different these gait patterns end up being. And here you can see him walking up some stairs, which is sort of similar to walking up the ramp, except that the foot height is placed very specifically for the stairs, and it's also a flat foot. You can also see just how much he's using his upper body to pull himself up this ramp. It's quite a bit of force. Mark is a very muscular individual, and so that makes this a little bit easier. But it's also something that we're working on addressing because these devices are very challenging to use. Both the Rewalk and Quicks require quite a bit of physiological demand. I exercise fairly regularly and have walked in both of these, and the entire time I'm just drenched in sweat and shaking because of how much energy it takes to use them. Which for people with spinal cord injury is not quite a reasonable request. So something that we're trying to do is figure out how to make these devices easier to use. We've got fantastic hardware platforms, and now the idea is to make them something that's effective for a wider portion of the population. And one of the options that we've been looking into is using haptic feedback for gait events. People with spinal cord injury don't have any sort of proprioception, so they have no idea where their feet are and can't feel them in space. And so Mark, most of the time, is looking down at his feet instead of being able to look at where he's going so that he knows if one foot's in the air, if he's in double support, these different types of situations. So the image on the left is his arm, and he's got small little vibrational motors at different spots. He's got 2 on his wrist and 2 at his forearm, and they trigger different events and give him cues for different events that are happening. So the one at his wrist will start vibrating when his toe off is happening, and he's got these on both arms, so he's able to tell what's happening for both legs. But the motor at his wrist starts vibrating when toe off occurs. And then it goes up to his forearm once his leg is in the air, and it starts wrapping around his forearm as he progresses through the swing phase. So it wraps around to let him know he's almost about heel strike, and then it gives him an indication when he is at heel strike. And this repeats on the other side so that he's able to understand what his legs are doing without having to look at them. And this next video really showcases him being able to see what's going on in the device without looking at it, and it's really exciting. So you can see with his hands, him understanding what's going on with the device every time it takes a step, where he's got heel strike and then foot flat. And then he understands that it's queuing up the next step, heel strike and foot flat. And it's just a very intuitive way for him to understand what's going on with his legs, and has given him a lot more understanding of what's going on. We've also been using this for a much more balance-related information. So Davin there is standing on a force plate, which is able to measure where he is in space, if he's leaning forwards or backwards, side to side. And Mark is getting cues on his arms for where that center of mass is. And you can sort of see him indicating where Davin is leaning further back or further to the left or further to the right. And he's able to get that information from his forearms. It's interesting because standing in an exoskeleton is a bit of a different coordination pattern than just walking in general, and learning how to balance in it is a very different situation. So having this kind of feedback is actually very helpful. And then the last thing I'm going to show on this is just how important the gait pattern is. So the difference between these two videos is very minor, where his legs are straighter during stance as well as swing. His knees aren't bending quite as far, but it's much easier for him to walk in the second video than it is for him to walk in the top video. And they were taken just a week apart. So it just shows how important different aspects of these gait patterns are, and how sensitive we are to what the device is doing. Typically, these exoskeletons are tuned to the individual through hand tuning. There's an operator and the pilot, and they talk back and forth for what is useful, what is not, let's tweak this or that. And this is a very slow process that has no guarantee of finding something useful, partly because it's just a massive search space to be able to see what can we do with these different parameters. So we're looking to fine-tune the exoskeleton assistance in the future. Through a strategy that looks a little bit like this. So I'm going to walk you through this, where we're able to measure user data, feed that into some sort of cost function, which basically means that we're taking user information and turning it into some number that is useful for us. And then we feed it into an optimization algorithm, which then updates what the device is doing. So then the user reacts to the device, and we continue through this cycle to iteratively figure out what is most useful with the device. We can use it, this is the user-centered design that Ken mentioned before, where we change what the device is doing in response to the user. And we can have this for different types of people, different exoskeletons, different gait situations as well. And what the device should be doing is going to be different for you than it is for me. So having it very fine-tuned to each individual will ideally be very helpful. And so I'm going to plug my graduate research a little bit, because that's what I did for the 5 years before I got here. This strategy is called human-in-the-loop optimization, where we take real-time human performance measurements, feed them into an optimizer, which changes what the device is doing. And so the device and human have this very symbiotic relationship, where what the human is doing affects the device, and what the device is doing affects the human. And so we can iteratively figure out how to best assist somebody by measuring the human response and then feeding that into the device. Which the experiments that I ran in grad school looked a little bit like this, where you've got somebody walking on a treadmill. You're able to measure their energy expenditure as well as apply exoskeleton torque with this end effector. So the human performance measurement comes from that metabolic cost. We could look at other measurements like walking speed or muscle activity, but for these experiments, we were really focused on how much energy the person is using in these different conditions. And then the device control law is really, what is the device doing? How do we tune what it's doing to best assist somebody? And we performed these experiments for different walking speeds as well as different worn loads. So we figured out what is the best case exoskeleton assistance when walking at these 3 speeds. We did it specifically for slow walking and figured out what was best for that, as well as medium and fast. So for reference, able-bodied adults tend to walk at 1.25 meters per second, just as a fun little number. We also looked at how does worn mass affect this, where we looked at no load, 15% of body weight, and 30% of body weight. And the no load condition and the medium speed condition were repeated between the two optimization strategies. And we did find very large metabolic reductions. I will walk you guys through this plot. On the y-axis, we've got how much energy is somebody using. In blue, it's the results for the slow walking. In green is the results for the medium speed, and yellow is the results for the fast speed. The lightest colored bar is walking in the exoskeleton, but no torque is applied at all. And so this is just how much is the exoskeleton increasing your energy? How bad is the device for you when it's not doing anything? The medium colored bar is walking with no exoskeleton, which is a bit of a baseline. Since this is a tethered emulator system, that difference doesn't mean a lot because it's not able to go out into the real world. And a device that is able to go out into the real world will have a different impact on you than this device will. And the darkest colored bar is walking with optimized exoskeleton assistance. So this is from all of that optimization experiment, what is best for the user. And for slow walking, we got a decent reduction, but for medium and fast walking, we saw roughly a 50% metabolic reduction for both of these speeds, which before we did these experiments, the largest metabolic reduction was right around 24%. So it's a fun little scoreboard moment. And then we did the same thing for different worn loads and saw fairly similar results. So in this plot, y-axis is the same thing where it's how much energy are you using, and the shades are the same information. The green is the no load, purple is the light load, and red is the heaviest load condition. And something kind of fun is this darkest colored red bar is a very similar height to walking with no exoskeleton and no load. So through this optimization, we made it feel like walking with 30% of your body weight felt like walking with no extra mass at all, which is very exciting. And I did mention the metabolic results before, but this is a plot that shows them a little bit better. So the y-axis for this is how much of a metabolic reduction are you seeing, and the different dots indicate different exoskeletons that have been published over the last 10 years or so. They represent different joints that are being assisted, as well as is it tethered or not tethered, where for this plot, best is further negative. That's the goal. And we've found through human-in-the-loop optimization that we have massive performance improvements with this strategy. So before we did the human-in-the-loop optimization, the largest reduction was right around 20%, and then afterwards we got to 37%. And the reason why it's different from the previous slides is because this is relative to the no exoskeleton condition as opposed to walking in the device with it turned off. So different denominators if you're mathy focused. Another fun thing is that what we're able to see, what we're able to feel for, oops, I touched the mic, but what we're able to feel is right around a 23% metabolic reduction. That's what we can notice when the device is doing anything. And before this, we weren't able to even feel what these devices were doing. But using this strategy, we were able to really increase our savings and be able to feel exoskeleton assistance doing something for us as we're walking. And we don't have to just look at metabolic cost. We could also look at any of these other options up here. I've mentioned muscle activity before. For people with spinal cord injury, looking at how much crutch force you're using could be a much more effective option to look at. We could look at comfort or even injury risk reduction. So there's a lot of flexibility with this approach, and we're just sort of starting to scratch the surface with it. And the injury reduction brings us to the next point of exoskeletons for industrial applications. This is going to be our final bit of information today. So we're working on an exoskeleton for tank farm workers. These individuals work in a toxic waste environment, so they do have to wear heavy PPE that's an air tank on their back. It's roughly 30 pounds, and they need to wear this to be able to breathe. It's also an aging workforce, so that additional worn mass results in injury risk potential as well as fatigue. So having something that helps to offload that mass from the user onto, say, the exoskeleton instead could be very helpful, could improve their quality of life, could also reduce how much injury they end up having. And that's really the goal behind this project, is to offload that mass and help these individuals have better quality of life. And this is the exoskeleton that we've designed for it. It's able to fit a fairly wide variety of people. It's got passive compliant hips, and then it's got motors co-located with the knees and hips, which I'm going to show you here and here. And this is our first version of this device. We're going to be iterating through and making it better and better as time goes on. So to walk you through a little bit more, we do have this compliant 3D printed hip, which it helps us to not have to have an explicit joint for hip internal and external rotation, which is this direction. And that's very helpful for turning and being able to, say, squat, for example, because you turn your toes out as you squat. We also have a passive joint for hip add-in abduction, which is this direction. And people are able to just move as they want. And then we have actuated hips and knees. So the motors are right beside the user's joints for both of those options. And then the ankle joint motor is all the way up at the hips. And this is because if you've got further distal mass, so mass closer to your feet, it uses a lot more of your energy to be able to move that. You can think about walking with ankle weights as an example, where it takes a lot of energy, a lot of muscle to be able to walk with these ankle weights. And so it's the same sort of motivation here, where we want to make the device impact people as minimally as possible. So we've put that mass up closer to the user's center of mass so that they don't have to be using as much energy to move with that. And we've also got everything integrated with this SCBA harness. So this is the typical harness that the Hanford Take Farm workers wear, and it's completely bolted into the device. We've been working on a controller called gravity compensation, where the device calculates how much torque it needs to apply to be able to overcome its own mass as well as the mass of the tank. And we're using pressure-sensitive insoles inside of the person's shoes to see how much mass they're carrying, where their center of pressure is, are they leaning further forwards, further back, and the device is able to react for what the user is doing as well as any additional mass. And here you can see Jared is squatting with the device. You can really see it turn off more than anything, where he didn't really realize how much the device was doing until it stopped helping him. And it's very entertaining to see when the device turns off just how much of a reaction people end up having. And it's a very similar thing with lifting your legs. He's got his legs in the air, and the device is applying torque to hold those up. And so then as soon as it turns off, his muscles just aren't quite active to be holding them up in place. So they do end up falling. And it's very entertaining because everybody ends up having this same reaction where you don't realize how much the device is doing and how much you actually need to activate your muscles until it stops doing anything and your leg falls and hits the ground. Another controller that we're working on is a virtual spring mode, where it's basically like there's a spring connected to your belly button and then also to your feet. So as you're squatting, it provides a little bit of an upwards force, just a little bit of resistance so that you're not having to use your legs quite as much. But then as you go up, it gives you a big boost so that it's a lot easier to do this activity. And here you can see both of us squatting with this controller and doing a lot of experimentation with it. Figuring out what those spring stiffnesses are is a challenge and something that we've worked through iteratively, and something that we can use the human-in-the-loop optimization to be able to really fine-tune for each individual. Because what is most effective for me is probably not going to be what is most effective for Jared, because he's got about 70 pounds on me, and we're just very different sizes. So for the future of AVO, which is our exoskeleton that I've been talking about, we've got a couple of ideas. And I'm first going to mention the VR that we've been working on, where we do have this virtual environment that showcases the Hanford Take Farm. You're able to see other people wearing this device. You can also see yourself wearing the exoskeleton and what it feels like and how, or what it looks like. We can have multiple people in this environment from completely different places. So we could have somebody from the Hanford Take Farm in this environment, and we could be here, and we could be having a conversation with them to see what's effective and what is not effective. We also want to use it in a virtual training sort of setting. The whole idea behind this project is to help mitigate any sort of injuries that these individuals experience. So one way of doing that would be to have a virtual trainer that's telling you when you have bad form. If you squat with your back instead of with your legs, for example, or lift with your back instead of your legs, this will give you some feedback to be able to tell you, hey, that wasn't very good, that was a lot of strain on your body, you need to make some adjustments. And so we can have that just as this second skin, which is sensing what you're doing and also giving you feedback. And this is something that's in development that we're working on. And we want to end up combining it with the exoskeleton as well, so that we have a very good understanding of what the person is doing, what their physiological state is, so that we can have the device account for that and adjust in as best of a way as possible. We're also aiming to assist with different DOE relevant tasks. We've really been focusing on squatting for the moment, but they also look at lifting and lowering, pushing and pulling, shoveling, as well as walking. There's a lot of lower back injuries that they're having to deal with, so ideally we'll be helping with all of that. And then finally, my favorite, human-in-loop optimization. We are aiming to fine-tune the device for DOE relevant tasks. And this is, once again, taking real-time user data. For this, it could be some sort of estimate of, say, joint load, what sort of forces are going through their back, and having the device update on a regular basis based off of an optimization function to be able to really best address and reduce that joint loading. I'm going to wrap up this whole talk by talking about sort of where I see exoskeletons going in the future. And you're going to see the exact same image once again, where we're looking for a system optimization instead of an exoskeleton optimization. Because exoskeletons are the combination of humans and this robotic device, which makes us very well suited to do this because we've got fantastic human performance personnel here as well as fantastic robotics personnel. And we're this very fun bridge in between the two where we get to take into account both specialties. And we want to do this for the hand-for-tank farm workers as well as with quicks and be able to use this information for as many different devices as possible. It is device agnostic, it's person agnostic, and it makes it so that we can get the device to work as best as possible in different situations. And for the long-term future, it's going to be very interesting to see the effects of long-term exoskeleton use. This is probably the number one question that I get when talking about these things is, will your muscles atrophy if you use this exoskeleton consistently? And the answer is we don't really know because we haven't done the research yet. There's a very solid chance that your muscles will atrophy, but there's also a chance that if you use this device, you're going to end up walking more than you would have without it. And so your muscles could be at a very similar spot. You may just be able to go out and do more, which could be very impactful for people who are homebound and not able to walk as much. If you use the same amount of energy in a day, but you're able to walk twice as far, that could enable you to do so many more things. And so once again, we can use these devices to augment user performance. I'm thinking in the future, these devices are probably going to be very clothing-like, where you can barely tell that they're there. I mentioned the soft exosuits earlier, and I think that those are the most likely at this point in time to come out and be something that's effective. And regular use could potentially prevent injury. People who have very intense tasks like these firefighters or the paramedics, their bodies have to undergo quite a bit of stress. And so if we can use a device to reduce that stress, it could help to mitigate it against any sort of injury. I also mentioned promoting healthy aging, so we could potentially use these devices to reduce joint loading. Through this optimization strategy, we could reduce how much load is felt through the joints, which could be impactful for people with osteoarthritis. On the other hand, we could use these devices in a resistive mode, so it's much more like an exercise device, and it could be used to help to maintain that healthy muscle mass. So by just having some low levels of resistance, do you guys remember the Skechers Shape-Up shoes? Yes, almost in a similar vein to that, where it's just regular use with a little bit of resistance can help you to maintain that muscle mass. And it could be something that's able to do both assistance and resistance, where if you're not using a lot of energy, it could resist you slightly. But if you're doing something that's a lot more physically demanding, then it'll give you a little bit of assistance and make it easier to accomplish these tasks. And then finally, I am very hopeful that these devices in the future can enable mobility. They could be used to help rehabilitate somebody after an injury, get them up and moving, and be able to maintain that muscle mass, as well as help people with a spinal cord injury. I've touched on this quite a bit, but I'm really hoping that these devices can be functional beyond the lab space, because right now you have to have somebody with you at all times. ReWalk and all of these other devices are FDA approved, but it's with a lot of contingencies, like you need somebody with you to be able to use it. So it's not providing quite the independence that we were hoping for yet. It's getting there, but it's not quite there yet. And I'd like to thank the exoskeleton team. They have all done fantastic work, and I'm very happy to be working with them. Thank you all so much. Do you have any questions? There's one in the back.
Just a general question as an engineer. How do you get the parts for these things? Do you make them in-house, or do you have to contract them out, or just how do you do that?
We do a bit of both. We have mills and lathes here. We also have the ability to do carbon fiber layups. Most of the parts that we get machined, we do get them machined out. We outsource them because it's faster and cheaper to do it that way. Yes.
You mentioned not being able to go to the soccer game because of your blisters. Do
Yes.
you now have some method of measuring what's going on with the skin and if there's any issues?
That's a great question. The blisters were really because of the boots in that previous device, so we've gone around it by changing to sneakers instead. But we don't currently have a way of measuring those interaction forces between the exoskeleton and the user's skin. And it's something that we're interested in because there's a lot of questions on how much shear force, so how much is there rubbing, and trying to mitigate against that. Yes.
Number one, you do know the SEC championships are here this week.
I did not.
They are. They're about 5 miles or 10 miles from here.
Good to know, thank you.
And it's a whole week of round robin of all the SEC championship teams in soccer.
Thank you. Thank you for clarifying.
Would you give me a guess as to what we ought to expect in these half a dozen areas that you talked to us about, let's look 5 years or 10 years, what you're an educated guesser, so please do that.
Yeah, so I think that we're starting to actually see exoskeletons as products, where I showed a couple of different startup companies, and they're starting to be at a point where we can have these be effective and go out into the real world. So Biomodem is a small ankle device. It was one of the ones I showed earlier, and they are able to help kids with CP, cerebral palsy, and are being used regularly. So I do think that we're going to start seeing these devices more and more regularly. One of the challenges is having the device intelligently switch between different types of gait conditions. So knowing if you're going up a slope versus down a slope, for example. And these are the challenges that we're working on. People are using machine learning quite a bit for that, which everybody loves to use machine learning for things. I think that we're going to be seeing single joint exoskeletons come out in the near future, and as time progresses, we're going to see larger and larger devices. Yes.
Good dodge, Mark. Yeah, maybe if this works out, Tom Brady will play another 10 years. Timing works out. He's
No
exercising.
promises. No promises.
So how did you decide to use the forearms as a location of the haptics? Is there an advantage of using the forearms versus like somewhere on the torso?
Great question. This was really from talking with Mark. So it was something that he wanted. He wanted it to be on the forearms instead of the torso. There is some interaction with the crutches in the torso. There's also interaction between the crutches and the forearms. But this ended up being just a very intuitive place. It also gives him a lot of forward and backwards. It's also a place where you're very sensitive. So bony landmarks, like your wrist, you're able to feel quite a bit more than places that are a bit more fleshy. Yes, Mark.
Great talk.
Thank
Gwen.
you.
Really fascinating. I guess the challenges of creating exoskeletons that reproduce or support some aspects of still comparatively simple human movements firstly highlights how complex the human body is in
Agreed.
terms of its ability to recreate, particularly skilled movements in different forms. Do you see a day in future where exoskeletons may be commonly used to reproduce and enhance human expertise, for instance? So, for example, in combat, are we likely to see soldiers wearing exoskeletons such that they go beyond normal human functioning capabilities?
That's definitely the goal, is we're trying to sort of create superhumans a little bit. but enhanced skill sets is a lot harder of a question because, like you mentioned, we're addressing very simple tasks. Walking is one of the tasks that we do, so we do it every single day, and it's something that we're struggling with figuring out how to assist effectively, which, like you mentioned, just shows how complicated the human is. So I think as our understanding of the human body gets better and what people are doing, we're going to get to a better place to be able to be much more skilled. Do you have a follow-up?
I have a very quick follow-up, actually. How much does it cost to build one of those? Just
Oh, a lot.
Is it? So it's not the type of thing I'll be able to get at Walmart then, I presume.
Not this
Two
one.
for one? 2 for 1?
Only if you're nice.
Time for 2 more questions.
Hey, Glenn.
Hey.
Really a great talk, and I appreciate it very much.
Thank you.
As far as the simple things, as we age, one of the first things that we fail at is balance.
Mm-hmm.
And that would seem like that would be a low-hanging fruit, that having something that would help you balance through those first few years of you getting into elderly would be something fairly simple. Have you worked on that or thought about that?
I do totally agree. Unfortunately, balance is a very complicated thing that we don't understand very well. This is one of the other, we don't understand how humans work quite enough to be able to assist them well enough. One idea is that resistance, so just helping people be able to maintain that balance on their own because we don't understand the internal cost function and how people are optimizing for themselves. So if we can help you maintain that muscle mass, because as you age, our muscles do atrophy and we're not quite as strong, we don't have the reaction times. But if we can keep that muscle mass up, we can hopefully help to prevent falls and keep people balanced for longer. Thanks. Yes.
So my question kind of follows in line with that, and I'm probably not smart enough to understand your response, but
Sorry.
I've been following IHMC for a long time, and I'd seen a presentation probably 10 years ago with some of the robotics, and that, watching some Boston Scientific, Sony, things they do with robotics, perhaps incorporating gyroscopes for balance issues, things like that. So it sounds like you're kind of addressing that, but so the other question that I would ask is, how much do you collaborate with other robotics entities and share information and leverage that?
Oh, quite a bit. So you mentioned the different robotics groups. Did you get to see the video that we published recently on our custom humanoid? That one's really exciting. There's a lot of pushing it around and she's able to recover and totally balance. Yeah, so we work very closely with the robot. We're in the same lab space. We're less than a Nerf dart throw away. And so we do interact with them. We also collaborate with quite a few different universities. We're very close-knit with Georgia Tech, and I also interact with my PhD advisor quite a bit. So we've got a lot of collaborations that we're building up and trying to continue.
But would that gyroscopic function be a possibility for balance? You know, when someone who can't walk at all, and now they're outfitted with a suit with an incorporated gyroscope that would at least maintain their balance, so hopefully wouldn't have to use those crutches. Is that feasible?
It's an idea that we're working on. So specifically for the spinal cord injury, we do have add and abduction actuated, so we should theoretically have the capabilities to be able to balance. Where it gets a little bit more challenging is we have a human in the system that does things that are unexpected. So in the videos of the robots that are able to take a step and recover, they sometimes end up being very jerky and abrupt in a way that wouldn't be safe if somebody was inside of that device, especially somebody who has had their muscles atrophy and is in a very weak state. So it's something that we're looking into, most definitely. It's just a little bit more challenging to work with a human within this system instead of just with a robot. I like the idea with the gyroscope, though. Thank you. Thanks, guys. I think that was the last one.